We humans have always wanted to know, what is life? What is the difference between living and non-living things? The answer to this will help us understand our place in this entire universe. About 65 years ago, the scientist Schrödinger asked whether physics and chemistry could explain life. Even today, scientists are searching for the answer to this question. We know that we are made of lifeless particles, dead molecules. But how these molecules come together to make us alive is still a great mystery today. Understand this with a very simple example. Suppose you find a running refrigerator in a field, a fridge that's working. You'd be surprised how it got there and how it's running without electricity. Looking closely, you find it's running on sunlight. The fridge keeps its inside cold, going against the laws of nature. But this fridge couldn't have arrived there on its own. Nature doesn't build a useful, neatly organized machine by itself. Nature always prefers to scatter and break things down. But a tiny germ or bacterium is many times more intricate than this fridge. This bacterium works like a small factory in which thousands of things operate together. The main job of this factory is to take energy and make more cells like itself. This is where science's biggest paradox, its biggest puzzle appears. The laws of science say that things should break down and become disordered, but life runs very neatly. It is highly organized. This book closes the gap between chemistry and biology. It shows that Darwin's law of the change of living things, Darwinian evolution, is actually part of some larger, fixed laws of science. A particular kind of steadiness exists in nature, a stability. Only by understanding this can we know how life began. Charles Darwin himself had already guessed that some larger scientific law lies behind the origin of life. Living things are very strange and remarkable. Our eyes or our body's cells are like the finest machines, like the ribosome, which is a factory that makes proteins. It's so small it can't be seen, yet it works very fast and with perfect accuracy. Living things also show an enormous variety of forms: a rose, a whale, a bacterium, all very different from one another. At the same time, living things make their own choices. A real dog and a toy dog might look alike, but the real dog acts on its own will. Non-living things can take any shape, like a crooked stone, but living things have a very fixed, precise structure. They are highly specific. Even a small change in our DNA can bring a deadly disease. There is a strict law of science, the second law, that says everything in the world moves toward decay. But our body keeps using energy continuously to maintain its structure, its order. That's why we eat. Darwin's law explains how a single cell became a human being, but it doesn't explain how that first cell came to be. The origin of life is not a question of biology, but of chemistry. How did life begin on its own from non-living matter? This remains science's biggest unanswered question. Living things always have a goal in science. This is called teleonomy. Every organism works toward its goal: building a nest, finding food, or reproducing. Non-living things, on the other hand, have no goal. They simply follow the laws of physics. A ball thrown up will fall down because of gravity. We live in two different worlds at once. When dealing with non-living things, we apply the laws of science like building a house or lighting a fire. But with humans or animals, our approach is different. We try to understand their behavior and their goals. No law of science can predict in advance a hungry lion's attack. This can only be understood through biology. We rely every day on other people's goals. When driving on the road, we assume others also want to reach their destination safely. This sense of purpose isn't found only in humans or large animals. Even a tiny bacterium swims toward food and away from poison. Without a brain, it still knows its task. Every organism's ultimate goal is to increase its numbers to reproduce. Non-living machines like a clock always stay the same. They are static. They keep running until some part breaks. But a living body is always changing. It's dynamic. Inside our bodies, cells and proteins are constantly breaking down and being rebuilt to keep the body in good condition. This means that within a few weeks, we become an entirely new person on the inside. There's enormous diversity in life. The world has millions of kinds of animals and plants, and even more countless tiny organisms, microbes that we cannot see. A single liter of seawater can hold more than 1 billion bacteria. How did so many different forms of life come about? This is still a great question today. Even Darwin's laws haven't fully solved this mystery of evolution. Life always exists in a wobbling, unstable state. Think of it like a bird that must keep flapping its wings to stay in the air. If it stops, it falls. In the same way, even a small bacterium must keep spending energy to stay alive. The law of science says everything in the world moves toward rest equilibrium. But cells do the opposite. They spend energy to maintain their chemicals. The biggest question is, how did life, restless, constantly spending energy, arise on its own from a lifeless, quiet, early Earth? Life's molecules have another strange property. A kind of handedness, like our right and left hands. These molecules also come in two forms. In nature, non-living matter is always split evenly, right and left, 50-50. But this isn't true of living things. All the sugars in our body are right-handed, and all the amino acids that build proteins are left-handed. This runs completely against nature's usual rule. Science still doesn't know how, in a 50-50 world, life made of only one kind of molecule began and how it has stayed that way ever since. We understand non-living things very well. We know ice, water, and steam are the same substance, just in different states. But we can't do this with living things. In ancient times, Aristotle believed everything in the world had a purpose. Later, science concluded the universe has no purpose of its own. In 1859, Darwin explained how organisms change over time, but he didn't explain how life first began, the origin of life. Even after major discoveries like DNA, we still haven't understood the true beginning of life. For years, scientists have tried to define life in a few words. In 1992, NASA said life is a system that sustains itself and changes over time. But this isn't entirely accurate. A mule, for instance, can't reproduce, so it doesn't fit Darwin's rule, yet it is still alive. This means squeezing life into one line is very difficult. To know what life is, we need not just a definition, but a solid, complete theory. Right now, we don't have one. But what does understanding really mean? In science, the oldest and most reliable way to understand something is induction, observing many events and finding the pattern or rule among them. This method is so simple, even a child uses it. If a child drops a toy, it falls. After this happens a few times, the child understands that things always fall down. This is a form of induction. Even your pet dog, seeing you open its food container, recognizes the pattern and knows it's about to be fed. Scientists do the same thing, just on a larger scale. Newton didn't just watch an apple fall. He also understood why the moon orbits the Earth. He found the larger law connecting these two events, which we call gravity. In science, no law is ever the final truth. Newton's laws were later refined by Einstein, so it's more accurate to call laws patterns that can be revised when needed. Science uses two approaches to understand things: reduction and holism. Reduction means understanding something big by breaking it into smaller parts, like understanding a clock by taking apart its components. Science's greatest successes have come through this method. In biology too, DNA and cells have been understood this way. Holism holds that a large system can't be understood just by looking at its small parts. When a system works together, new properties emerge that aren't present in the parts alone. Water is wet, but hydrogen and oxygen gas alone aren't. So holism says we should look at the whole system together. These two approaches are debated, but in truth, holism is itself a larger form of reduction. Understanding a complex system like life needs both approaches. To know how life began, we need to understand the connection between chemistry and biology, how small, lifeless molecules come together to form a living, complex system. Thousands of chemical reactions happen continuously in every living thing. To understand life, we must first understand how and why these reactions occur. Any chemical reaction always moves downhill. Weaker substances combine to form a more stable one, which has lower energy. For example, hydrogen and oxygen gas combine to form water, which is more stable than the two gases, so this process can't reverse on its own. This is a crucial law of science, the second law of thermodynamics. But forming water still needs a small initial input of energy, a spark called the energy barrier. A process happens only if the resulting product is more stable than the starting reactants. Another law of science says things always prefer to scatter to become disordered. This is called entropy. If you throw bricks on the ground, they won't land in a neat pile, but scattered about. So when a large molecule breaks into smaller pieces, it becomes simpler and more stable. Most chemical reactions are helped by a third substance, a catalyst, which doesn't change itself but speeds up the process. In our bodies, these are called enzymes. But there's a special kind of process called autocatalysis, where the substance being formed helps make more of itself. This grows very fast exponentially. Think of grains of rice doubled on each square of a chessboard. By the 64th square, the rice would cover the entire Earth. Similarly, particles or molecules that copy themselves self-replication are considered the biggest reason life began. DNA and RNA work this way. Stability is of two kinds. One that never changes, static, like water or a mountain, and another that keeps changing, dynamic, like a river or a waterfall. A river stays the same even as its water keeps flowing and changing. Life steadiness is of this second, dynamic kind. No organism lives forever, it dies. But before dying, it produces new organisms like itself. So the population always continues. This is called dynamic kinetic stability. Remarkably, this ever-changing steadiness of life can be more durable than even static things. A mountain might be perhaps 60 million years old, but a particular type of bacteria, cyanobacteria, has been alive on Earth for the past 3 billion years. This means there are two different worlds, even within chemistry. One where things are calm and settled, static, and another where things keep replicating and changing. Life belongs to this second kind of chemistry. The most essential rule of staying alive is things that can sustain themselves, that are stable, persist. Those that cannot, disappear. Even among non-living things, chemicals always tend to change into more stable forms. That's the second law. Hydrogen and oxygen combine into water because water is more stable than the two gases. But molecules that can copy themselves, replicators, follow different rules. For them, stability doesn't mean sitting quietly, but rapidly making more copies of themselves. The rule is, self-replicating chemical systems will always change into whatever form can copy itself faster and better. This rule resembles the rule of the living world but works differently. Evidence for this came from an experiment in the 1960s. When RNA molecules were left to copy themselves, mutations, copying errors, eventually produced smaller RNA molecules. These smaller molecules copied themselves faster and gradually replaced the longer, slower ones. This was a purely chemical process, no biology was involved. It proves that change and evolution can happen even in chemistry. Now, how do these two laws of science work together? Think of Russian nesting dolls, one inside another. The outer, largest doll is the big law within which the whole world operates. But things that copy themselves are like the inner doll, following their own special rules. If your car breaks down, it's true to say this happened because of the larger laws of science, but that won't help you fix the car. For that, you need to understand the rules of the machinery inside the engine. Now, to the biggest question, how did life begin on Earth? There are two parts to this. First, what happened? The historical question. What chemicals existed at the start, and under what conditions did they turn into living cells? Second, why did it happen? The ahistorical question. Which law of science caused non-living matter to take the form of life? If we know the answer to either question, finding the answer to the other becomes easier. But the trouble is, we still haven't found a clear answer to either. Earth is about 4.6 billion years old. The oldest fossils are 3.4 billion years old, but they belong to fairly advanced cells. They don't tell us how the first cell was formed. Another method is building a family tree of organisms by examining DNA and proteins, which helps us understand relationships between different life forms. But this method too hasn't given clues about the earliest life, because in ancient times, organisms exchanged genes not just with parents, but with others. to horizontal gene transfer. So it's very hard to determine who the very first organism, LUCA, the last universal common ancestor, was, and what it looked like. So we must search for clues to the origin of life within chemistry itself. How did life begin? This is a huge question for science. In the 1950s, Stanley Miller performed a famous experiment. He assumed that early Earth had gases like hydrogen, ammonia, methane, and water vapor. He passed electricity through these gases, simulating lightning from the sky at that time. The result was startling amino acids. The building blocks of proteins were formed. It seemed understanding the origin of life would be easy. But this excitement didn't last, because scientists then asked, where did life begin? In the deep sea or in soil? Was there carbon dioxide in the air at that time? These questions got different, tangled answers. The biggest problem was that we simply don't know what Earth's actual conditions were like billions of years ago. When we don't know what chemicals existed at the start, saying what could or couldn't have happened is just a guess, pure speculation. Some scientists have said that if RNA components, nucleotides, can't be made in the lab, that means they couldn't have formed on their own in nature either. This is flawed thinking. We can't say that something we haven't managed to do in the lab today could never have happened anywhere on Earth over millions of years. In fact, some scientists, thinking differently, have recently managed to make these components in the lab too. Even if we gave today's smartest scientists all the chemicals and equipment and asked them to build a living cell, they still couldn't do it, because we still don't know how life is actually built. So simply discovering which chemicals existed long ago can't by itself solve the mystery of life. There are two schools of thought in science. One says self-copying molecules like RNA came first. The other says an interconnected cycle of chemicals, a metabolic cycle, came first. But both share the same flaw. The second law says things prefer to scatter and settle down. So how could such a neatly run, continuously energy-spending thing as life have begun? Was life on Earth a coincidence? Or was it bound to happen by the laws of science? We don't know the true answer. We can predict whether it will snow on a mountain because we know the weather there. But we don't fully know what happened on Earth billions of years ago. And because we have only one example of life in the entire universe, our own Earth, we can't say for certain that life beginning is a common occurrence. It may be a very rare event. Biology today faces three big questions. What is life? How did it begin? And can we create it ourselves? These three questions are interconnected without answering one. Answering the other two is impossible. Over the last 60 years, discoveries like DNA have told us a lot about life's components. But what life actually is remains a mystery. The famous scientist Carl Woese said today's biology is like physics 100 years ago, which believed everything had already been discovered, but in reality, it knew very little. Darwin explained how organisms change, and later, science discovered that genes drive this. When the human genome was fully sequenced in 2000, people thought the puzzle of life was solved. But the truth is, reading all 3 billion letters of the DNA code still didn't give us a complete understanding of life. We can see the trees, but not understand the whole forest. Life's biggest puzzle is its structure and complexity, its organizational complexity. Science's old method of reductionism, breaking things into small parts, doesn't work here. So scientists are adopting a new approach called systems biology, which focuses on how a cell's different parts work together as a system. But even this approach hasn't answered some of life's deeper questions. When science can't explain something difficult, it often dismisses it by calling it an emergent property. Because of this, the question of why life has a purpose has been almost forgotten by science. Besides biology, physics and mathematics have also tried to understand life. In physics, there's a principle called non-equilibrium thermodynamics, which explains how things like water vortices can form structure without any outside help. Some thought life might have begun this way too, but this gave no definite answer. In mathematics, there's a simulation called the game of life, which shows how simple rules can create very complex patterns. This helps us understand how complexity forms, but it hasn't unlocked the real mystery of life. In the end, to understand life, we need to build on the older methods of biology, physics, and mathematics. Biology's biggest puzzle is its complexity. Is the old scientific method reductionism, breaking things into small parts enough to understand it? Some scientists say no, but I believe this method is still useful today. By combining Darwin's law with chemistry, we can show that biology is really just a branch of chemistry, one connected to self-copying chemicals. Systems chemistry is a new field working to solve this puzzle. It works bottom up, trying to understand the journey from the simplest early chemicals to today's complex organisms. We believe life began from very simple things. So if we want to understand a Boeing 747, it's more useful to study the Wright brothers' first simple airplane than the 747 itself. Similarly, to understand today's organisms, we need to understand the older, simpler, self-copying molecules. We believe Earth's journey of life happened in two parts. First, when life formed from non-living matter, the chemical phase. Second, when simple organisms became today's complex organisms, the biological phase. But really, these aren't two separate phases. They're one continuous process. An experiment in the 1960s showed that RNA molecules change themselves over time too, meaning Darwin's law applies not just to organisms, but to chemicals as well. Another rule in biology, the competitive exclusion principle, says two organisms competing for the exact same resource can't coexist. The fitter one will eliminate the other. The Galapagos finches with their different beaks are the best example. They survived by eating different kinds of food. Interestingly, RNA molecules do exactly the same thing. When two different RNAs were given the same substrate, the faster one eliminated the other. But when given 5 different substrates, both claimed their own share and survived together, just like those finches. Life's whole journey is one of increasing complexity. At first, when a lone molecule tried to copy itself, it was slow and weak. But when two different molecules began helping each other, cross-catalysis and cooperation, their work became much faster and easier. In biology, This is called symbiosis, meaning what we can't do alone, we can do very well together. According to the laws of science, we should always understand bigger, more complex things, biological ones, through simpler, smaller things, chemical ones, not the other way around. So it's more accurate to understand biology's natural selection through chemistry's kinetic selection, meaning simply, whoever is faster wins. Chemistry can explain, more deeply and mathematically, which molecule will eliminate another faster, or how they can coexist. So we can say biology and chemistry are two sides of the same coin. Darwin said the fittest organism survives and reproduces survival of the fittest. But what actually is fitness? In chemistry, we call this dynamic kinetic stability, or DKS, meaning how quickly a system can make copies of itself and how long it can sustain itself. In biology, we never look at the fitness of a single organism, but of the whole population. No organism lives forever. Organisms are born and die, but the population endures. So true fitness lies hidden in the population's steadiness, its DKS. This stability can differ for each organism and can change when the environment changes. For example, bacteria multiply very fast in water, but if chlorine is added, they all die their stability. Their DKS becomes zero. Evolution's biggest rule is that organisms always move in the direction where their stability, their DKS, is highest. Whichever organism, whichever replicator can grow its population most effectively will survive. This rule applies to everything, from non-living matter to today's large, complex organisms. This means the origin of life and biological evolution aren't two separate things. Both are driven by the same rule, DKS maximization. Natural selection is just one path that helps organisms reach this destination. Evolution has four main steps. First, self-copying replication. Second, changes in the copy mutation. Third, the system becoming more complex and better complexification. And fourth, the best one being chosen selection. The information in DNA actually works like a very precise chemical, a specific catalyst. This information doesn't just copy itself, but also helps build other essential chemicals, proteins. As evolution progressed, DNA kept refining itself to increase its DKS, its stability. There's a strict law of science saying everything must scatter and settle over time, but the world of organisms runs on a different rule, DKS, that stops them from scattering. How can these two different laws operate at the same time? The answer is energy. If an organism, a replicator, learns to draw in energy from outside through metabolism, through energy gathering, it can also overcome this law of science. Think of it like a car that can only go downhill because of gravity. But if it has an engine and is given fuel energy, it can climb uphill too. The day some lifeless molecule on Earth developed the power to draw in energy metabolism, that was the day life began. There's been a long debate over what came first, the self-copying particle, the replicator, or the energy-producing system metabolism. In truth, both work together. Without energy, without metabolism, a molecule can't copy itself. And without copying, energy has no purpose. Both must exist together for life to begin. Now let's find the answer to life's biggest question. What is life? To answer this, we need to understand a new field of science called systems chemistry, which tells us how life began from simple, non-living chemicals. At the start, some molecule formed on Earth that could make more of itself. This molecule was very small, but held enormous power, the power to grow its population rapidly, exponential growth. If a small molecule copied itself every minute, it could fill the entire universe in just 5 hours. Because of this power, a new rule applies in the world of organisms: Dynamic Kinetic Stability, or DKS, meaning whichever chemical copies itself fastest will be the most stable. This is where the definition of life comes from. Life is a system that gathers its own energy, continuously copies itself, and sustains itself a self-sustaining, kinetically stable, dynamic reaction network. By this definition, death simply means that an organism has left this self-copying, replicative world and returned to the calm, ordinary world of chemicals, the thermodynamic world. Life isn't some impossibly difficult puzzle. It's just a continuously running cycle. Organisms copy themselves. Replication. Changes occur in them. Mutation. They become better. Complexification. And the best one is chosen. Selection. Life's enormous complexity isn't the cause of life. It's the result of this ongoing copying process. Now let's understand some of life's special features through this new rule, DKS. First, why is life so complicated, so complex? Non-living things combine because they want to become stable. But in the world of organisms, things combine so they can copy themselves faster. As organisms improve, they became more complex to further increase their steadiness, their stability, their DKS. Second, why are organisms always wobbling, unstable? The second law says things should settle down, but organisms must keep spending energy to copy themselves. Just like a bird must keep flapping its wings to stay in the air. It's this energy-gathering power metabolism that lets organisms stay alive despite being unstable. Third, why do organisms keep changing? Why are they dynamic? An organism's body keeps breaking down and rebuilding, so the population can continue, just like a waterfall's water keeps changing, while the waterfall itself remains. Death, too, is a necessary part of this cycle, clearing away the old to make room for the new. Fourth, why is there so much diversity of organisms in the world? Ordinary chemicals always want to reach a single destination, a thermodynamic sink, but organisms have many different ways to improve themselves. They adapt to their surroundings and available resources, which creates new organisms. Fifth, why does life contain only one kind of molecule? Non-living matter has equal amounts of right and left-handed molecules, but life has only one kind. This is because the fast copying process, autocatalysis, favors one kind of molecule. Having only one kind lets organisms copy themselves faster and with fewer errors, increasing their steadiness, their DKS. Sixth, why do organisms seem to have their own goal, their own teleonomy, their own purpose? Ordinary chemicals can only flow downhill, but once an organism learns to gather energy, it can also go uphill, like a car engine. It's no longer just a slave to the laws of science, it works to preserve itself, for its DKS, which appears to us as a purpose. Now, for a few more important questions. What is consciousness? The power to think and be self-aware. Consciousness, or self-awareness, exists only in more advanced life forms. Just as evolution used bones to strengthen the body and eyes to see, consciousness too is a way of increasing an organism's steadiness, its DKS. To understand this, we'd need to go far back and study the simplest early forms of neural activity. Would alien life look like us? If there is life elsewhere in the universe, it too would be built on these same rules, the rules of chemistry. It's not necessary that its body be made of DNA or protein. Some other chemical could serve the role of self-copying, but interestingly, if such life exists, it would work in essentially the same way we do, just as every car has an engine, wheels, and a seat, whether made of steel or fiber. Similarly, alien life forms would use the same strategies to preserve themselves and copy themselves that Earth's organisms have discovered. Can we create life in a lab? This is very difficult. It's much easier to kill a living system than to build one. Think of it like this: a man juggling 5 balls in the air. It's easy to knock the balls down by pushing him, but if you throw 5 balls at him all at once, he won't suddenly start juggling them. Life, too, is a continuously running process, a dynamic process. You can't create a living cell just by mixing all of a cell's chemicals together. To build it, you'd have to proceed step by step, exactly as evolution did over billions of years. So, how did life begin? What is the origin of life? Systems chemistry has given us the real answer. Life began simply because some chemicals, some simple compounds, started copying themselves. As they kept copying, they kept improving and becoming more complex in order to remain more stable, more steady. Darwin's theory of evolution applies not just to animals, but to chemicals too. Darwin had guessed 130 years ago that biology and chemistry are two sides of the same coin. Life isn't a single thing, it's a web of chemicals, a network, and water is the place where this web was woven. We think every organism has a separate identity, but the truth is, no organism is truly alone. A human body has 10 times more bacteria than its own cells, and these keep it alive. Trees, too, depend on soil bacteria. Life is like a set of Russian nesting dolls hidden within one another. We are all part of one large family. Even a mule, which can't reproduce, or viruses, which can't survive on their own, are part of this same large web, this same network. Biology and chemistry have become one. This understanding shows us how we are part of this whole universe, and how all living things are connected to one another. This very connection may become a new source of hope for the future of humankind. That's all for this book. We'll meet again in a new episode with a new book. You were listening to Think Again. Thank you.